Hello and welcome to our sixth lesson on integration. In the previous lesson, we learned that we can determine the area bounded by the curve and for the provided limit of x is equals to a and x is equals to b. Let's say, for example, we are to determine the area under the curve y of x for the limits of x is equals to a and x is equals to b. So that region is the one that is shaded as indicated on the diagram. So for us to be able to determine what that area is going to be, we saw that what we need to do is to take the integral of the curve y of x with respect to dx and evaluate the resulting integral for the limit of x is equals to a and x is equals to b. And therefore, it can be given by the expression of a is equals to the integral from x is equals to a to x is equals to b of y dx. Note that you can also be able to determine the area bounded by the curve g of y for the provided limits of y is equals to a and y is equals to b by using the expression area is equals to the integral from y is equals to a to y is equals to b g of y dy. And again, just like in the case where we have y of x dx and then evaluating the integral for the provided limits, is the same case when now the curve that you've been provided, it's a function of y. You integrate that particular curve with respect to y and evaluate the resulting integral for y is equals to a and y is equals to b. Now, in this lesson, we'll be looking at the area bounded by a curve and a line and between the provided limits. And let's take a very fast example to help us understand how we're able to determine this particular area between a curve and a line and for the provided limits. Find the area enclosed by the curve y is equals to 9x minus x squared and y is equals to x. So the diagram on the side of the screen illustrates the area or the region whose area we need to find, which is bounded by the curve y is equals to 9x minus x squared and by the line y is equals to x. So for us to be able to determine what that area is going to be, remember we need to have the limits within which we are going to integrate our curve and evaluate the integral for the provided limits for us to be able to determine that particular area. So therefore, to find the limits of integration, we find the coordinates of the point of intersection between the curve y is equals to 9x minus x squared and the line y is equals to x. At the point of intersection, y equals to x will be equated to the equation of y equals to 9x minus x squared, and therefore that will be able to give us 9x minus x squared being equal to x. And we can use that particular equation to solve for the value of x at this point of intersections, and that is going to give us x being equal to 0 or 8 minus x being equal to 0, and that will mean that our x is equals to 8. Now we can substitute each of these values of x in n of the two equations, either this one or this one over here. We can find the corresponding coordinate of y, and for instance, if we were to substitute in the first one using x is equals to 0, we are going to have that y is basically equal to 0, and therefore the first point of intersection becomes 0, 0. And then for the x is equals to 8, again substituting in this first equation over here, we are going to have y is equals to 8, and that means the other point of intersection is going to be 8, 8. Now with these 2 points of intersection, we can be able to determine the limits within which you're going to integrate both the curve and the line to be able to determine the area bounded by the curve and the line. And therefore, the limit of integration becomes x being equal to 0 and x being equal to 8. Now, the required area is found by subtracting the area under y is equals to x from the area under y is equals to 9x minus x squared. Remember, when you integrate the curve y is equals to 9x minus x squared between the limits of x is equals to 0 and x is equals to 8, it gives you the area below that particular curve, and the y and the x-axis. And when you integrate the line y is equals to x for the limit of x is equals to 0 and x is equals to 8, it gives you the area below that particular line and the x-axis. So therefore, for us to be able to determine the area that is between bounded between the line and the curve, you need to find the entire area under that particular curve, subtract the area under the line, and it will be able to give you the required area. So therefore, we are going to have the integral from 0 to 8, 9x minus x squared dx, and then we subtract the integral from 0 to 8 over x dx. So what you're going to have is that the integral for the 9x minus x squared dx is going to give us 117 and a third, and that of x dx from 0 to 8 is going to give us 32, and therefore the difference between the two gives us 85 and a third square units, which is the area that is bound by the curve y is equals to 9x minus x squared and the line y is equals to x. In general, to find the area between a curve and a line, the following steps are usually taken. Step number 1 is to determine the coordinates of the point of the intersection. And then step number 2 is to use the x coordinates of the point of intersection as the limit of integration. And then step number 3 is to integrate the line for the area under the line. And then step number 4 is to integrate the curve for the area under the curve. And then lastly, the fifth step is to subtract the areas to get the area of the required region. Our example number 2, find the area bounded by the line y is equals to 4x, the curve y is equals to x squared plus a half x, and the x-axis. Now the region whose area we wish to find is indicated on the diagram on this other side of the screen. And you notice that the point Q is the point of intersection, and also the other point of intersection is at the origin. So the required area will be found by first identifying the lower and the upper limit within which you're going to integrate the line and also the curve for us to determine what that area is going to be. Since point Q is a point of intersection, then at that particular point, the line and the curve will be equal, and therefore we can equate their equations. And so you're going to have x squared minus a half x is equals to 4x. And we are going to have the expression x squared minus 4 and a half x is equals to 0. So x being common, we shall factor out, and that will give us x into x minus 4 and a half, as indicated over here, and then equated to 0. So that means x is equals to 0, or x minus 4.5 is equals to 0, implying that x is going to be equal to 4.5. So using n of the two equations again, if you wanted to find the coordinates of y, we can be able to find what the coordinates of y are going to be for the 2 points of intersection. But since that isn't really so important, we only need to take note of that the x is equals to 0 forms the lower limit, and the x equals to 4.5 forms the upper limit, within which you're going to integrate and find the area that is bounded by the curve and the provided line. Area of the required region will be given by area is equals to the integral from 0 to 4.5, 4x dx, and then we subtract the integral from 0 to 4.5, x squared minus a half x dx. So working out the first one, you're going to have 4x squared over 2 plus the arbitrary constant c, and then evaluated from 0 to 4.5, which shall give us 40.5 square units. And then we also work out for the second one, which is going to give us x cubed over 3 minus a half x squared over 2 plus the arbitrary constant c. Again, evaluating for x equals to 0 and 4.5, which is going to give us 30.375 minus 5.0625. And ultimately, the difference between those two areas is going to give us 15.19 square units. And therefore, that becomes the area that is bound by the curve y is equals to x squared minus a half x, and the line y is equals to 4x. It can be noted from the example number 1 and also example number 2 that when you're told to determine the area bound by a curve and a line, It involves you determining the area under the curve and also the area under the line and getting the difference between the two areas. Also, it is possible that we can find the area that is bound by any two curves, and it also involves integrating the two curves individually for the indicated limits and finding the difference of the resulting areas. Now, in example number 3, it illustrates this point. We are told use the diagram below to answer the following questions. The first part of this question is to determine the coordinates of P. The second part of the question is to calculate the area bound by y is equals to x squared, y is equals to minus x squared plus 8, and the x-axis and also the y-axis. To find the coordinates of the point P, we note that at the point of intersection, the two equations will be equal, and therefore we equate them, which will give us x squared is equals to minus x squared plus 8. And we therefore solve for the value of x, and that is going to give us x being equal to negative 2 or x equals to positive 2. Now we shall ignore negative 2 since the coordinates of P are on the positive side, and therefore we can also be able to determine what the value of y is going to be by using x is equals to 2 and substituting in n of the two equations. Now if we use the equation y is equals to x squared, then you're going to have the coordinate of y being equal to 2 squared, which gives us 4, and therefore the point P will have the coordinates 2 and 4. The area of the required region becomes the integral from 0 to 2 minus x squared plus 8 dx. We subtract the integral from 0 to 2 x squared dx. So for the first one, you're going to get minus 8 over 3 plus 16. And then we shall subtract for the second one, which is 8 over 3. And that is going to give us 10 and 2/3 square units. Time to put to practice what you've learned in this lesson. Pause the video and try to work out the following questions. That's all for now. See you in our next lesson.